In this video, we're going to be starting the chemistry of life notes. We've got some labs that can help you out with some of this chemistry. Crash Course has some good videos that can help you out with this. So does Khan Academy. So if at any point you're struggling with the chemistry material, please make sure you get the help that you need. Some students are just awesome at this. They had a great teacher in high school and they know what's up with chemistry. And some students have never had this before. And so some students need a little bit of extra help. If you are one of those people, just please make sure you get it one way or another. Remember that I'm always here to answer any of the questions that you have. To start out in this chapter, we have the question, what is matter? The definition they usually give you in like middle school and high school is it's anything that has mass and takes up space. What is matter composed of? It's made up of elements, which you can find in the periodic table, stuff like oxygen and hydrogen and all of those nice little things that give some people some flashbacks to middle school. What is the chemical symbol, which is also sometimes called the atomic symbol? That's the 1 or 2 letter abbreviation for each element. Like if you look up most periodic tables, they just have abbreviations for the elements. That's what the atomic symbol is. So this is beryllium, magnesium, calcium, and so on all the way off down. You're not going to have to memorize all of these. We're really only going to be talking about the first few what are known as periods on the periodic table. That's a row. The rest of these elements aren't really all that important when it comes to biology, and so we're just not going to spend a lot of time talking about those. But for the elements that we do talk about in those first few periods, you should become familiar with those abbreviations, and so I would recommend making some flashcards, put the full name on one side and put the symbol on the other, just so you can practice it. There's probably a Quizlet out there for that as well. Usually in class I have you guys practice this and I throw out element names and then I have you write down the atomic symbol. You can't really do that in an online setting like this, so once again, do some flashcards or something just to practice. Atoms can bond together to form what? They can form molecules. The oxygen that you breathe in isn't just an atom of oxygen, it's molecules of oxygen, which is 2 oxygen atoms that are covalently bonded together. A water molecule is H2O, so that's 2 hydrogen atoms and 1 oxygen atom. So molecules, those are the things that you can build up from atoms. We did also mention this a little bit back in chapter 1. Okay, the subatomic particles. The statement says all atoms contain 3 subatomic particles. What are they and what are the features of each? This table shows you what are they? Proton, neutron, and electron. What are the features of each? What's in this table is what I want you to know. I might add something, we'll see what's in the table. So you need to know that protons have a positive charge. They have an atomic mass of 1. The unit for that is either AMU for atomic mass unit or Daltons. I don't care which one you want to use there. Protons can be found in the nucleus of an atom. Neutrons don't have a charge. They also have an atomic mass of 1, and they can also be found in the nucleus of an atom. The nucleus happens to be the central core. So as you look at the picture up here, these are 2 protons, these are 2 neutrons. They make up the nucleus of this atom. Then for the final subatomic particle, it's an electron. It has a negative charge. Its mass is so small we usually just consider it to be 0. They are not in the nucleus. Instead, they are outside in areas that we usually call clouds or shells or orbitals or energy levels. It's one of those things that has a bazillion different names. I'm perfectly fine if you want to call it an electron shell. I think I tend to call them orbitals more often than not, but again, whatever you want to call them, I'm pretty much happy with. Define the atomic number. The atomic number is defined as the number of protons an element is going to have. You can look up an atomic number and find out what element that is on the periodic table. For example, this is helium. Helium always has an atomic number of 2, which means every helium atom on the planet has 2 protons that exist within the nucleus. Now the atomic number can also sometimes tell you the number of electrons that an atom is going to have, as long as it's electrically neutral, which helium usually is. So that means that not only does helium have 2 protons, it usually has 2 electrons that are circling the nucleus as well. So again, the definition is it's the number of protons, so it will always tell you how many protons an atom has. It usually also tells you how many electrons an atom has. Carbon has an atomic number of 6. What does that mean? If you go back to the definition, the atomic number tells you the number of protons, so what does it mean? It means a carbon atom has 6 protons in it. Now, based on the other thing that I just said, it also means that usually carbon is going to have 6 electrons that go around the nucleus in those orbitals that we were talking about earlier. define the mass number. Mass number and atomic weight are similar, but they're not exactly the same thing. If you look it up on a periodic table, the atomic weight is a number that has a decimal point that comes after it usually. Let me pull out a periodic table, not that you guys can see what I'm looking at. Helium, if you look at the periodic table, it has an atomic weight of 4.00260. If you round that to the nearest whole number, that would give you the mass number. So 4.002, that would round to 4, which means the mass number for helium is 4. Now what that's telling you is that an atom weighs 4 atomic mass units. If you think back to which subatomic particles have weight, that's protons and neutrons. So here's what we know. Couple of extra things, and I need to make sure I switch my thing on so that I can write. I'm going to do it in this color because I'm feeling purpley today. This is the atomic symbol. It's just the abbreviation for an element. This one is the abbreviation for helium. To the lower left of that atomic symbol, this is where we write the atomic number, which tells us how many protons an atom has and usually how many electrons it has. The mass number is written to the upper left of the atomic symbol, and it tells us how many protons and neutrons an element has. So what we can do is a little bit of math, and if we are given this information, we know exactly what that atom actually contains. So for example, helium has an atomic number of 2. We know that it's going to have 2 protons in it, and so we can do 2 positive protons inside. We know that the atomic number is usually going to tell us the number of electrons. Electrons circle in an orbital, and they have a negative charge, so we could doodle 2 little electrons in that. We have to do a little bit of math to figure out how many neutrons it has. So the mass number tells us how many protons and neutrons. This tells us how many protons. So if we just subtract and set that up as a problem, dang it, it's going to get weird on me again. Then that means 4 minus 2 protons, there must be 2 neutrons present inside the nucleus of that atom. So we could draw 2 neutrons, and they don't have a charge. And so that is what a helium atom looks like. Next, carbon has a mass number of 12. What does that mean? So we said earlier that carbon has an atomic number of 6, so it must have 6 protons. This question says it has a mass number of 12. So what does that mean? Well, we already know that that 6 means it has 6 protons, and you can see that right there. 12 minus 6 will tell us the number of neutrons, and so that would be there's 6 neutrons, and that's what that says. Now, while the mass number doesn't tell you this, the atomic number does. You can also see the electrons that are circling around there, and there's 6 of those in there as well, so they've labeled that right there for you. Okay. What we usually do at this point in the class is we do some practice problems to make sure you really understand what's going on. I might have to back out of here to give myself a black screen, so give me just a second so that I can do that. Let's see, I'm going to do it after this one. And I'm going to come back here so that we have it. Okay, so practice problem. Let's say we're going to ask you what's the atomic symbol for hydrogen. At some point you're going to have to know that. So hydrogen's atomic symbol is, oh, I forgot to put my ink back on. Let's see. Let's do, I don't know, I'm feeling greenish now. So that is the atomic symbol for hydrogen. Now, ordinarily I give students a copy of the periodic table. You guys can just Google periodic table and find one, and you should be okay. That way I don't have to put one in Blackboard for you guys, but all periodic tables have the same information on them, so you're fine there. Now hydrogen, if you look at a periodic table, it has an atomic number of 1. Once again, if you're still looking at a periodic table, it has an atomic weight of 1.00794. You would round that off to the nearest whole number, so the mass number is also 1. Now, if you were to have this information, you should be able to draw the full atom. So, remember, this is the atomic number. It tells us how many protons are in the nucleus of an atom. Also tells us how many electrons are circling around there. And so we can draw an electron there too. We've got to do the math to find the number of neutrons. 1 minus 1 tells us there are no neutrons in a typical hydrogen atom. So this is the full atom. There's another way that you can depict atoms that make it easier to understand how they're going to bond with other elements. It's called a Lewis dot structure. To do a Lewis dot structure, you do the atomic symbol, which was H for hydrogen, and then you put a dot around that for every electron that's in the outermost shell of that element. So there's only one shell or one orbital around hydrogen, and it has one electron in it. That means a hydrogen is going to get one dot. So that's the Lewis dot structure. So this information, you can get all of that on the periodic table. If you have this information, you should be able to draw the atom, and you should be able to figure out the Lewis dot structure, which is the symbol plus a dot for each electron in the outermost shell, which that is supposed to be one dot. I don't know why it tried to make it more than that. There you go. One little dot outside of that. So that's hydrogen. Okay, for our second element, we're going to do oxygen. Oxygen has the atomic symbol, where did my thing go? There we go, of O. So we're going to put an O up here. We look at the periodic table to find the pertinent numbers, and if you look next to the O, it has an atomic number of 8. If you look at the atomic weight, it's 15.99. That would round up to 16, so it has a mass number of 16. From there, again, we should be able to draw an atom. Now I'm going to start abbreviating some things instead of just drawing a whole bunch of circles. So if we were going to draw the atom inside the nucleus, it would have 8 protons. I'm going to abbreviate that like that, and 8 plus for 8 protons. Now we're going to place the electrons, because we know that that 8 also tells us how many electrons are going to be contained within an atom. The thing about electrons is they exist in orbitals, and each orbital can only hold a certain number of electrons. So here's the first time we're going to do this. You always start filling in the innermost ring, and that electron orbital can only hold 2 electrons. So coming over here to the oxygen, it's going to have 8 electrons, but we can only put 2 of those in the innermost ring. So we still have 6 more electrons we have to do something with. What we would do is we would move out to the next electron orbital. It can hold up to 8. We only had 6 more to place though, so we're going to go ahead and draw that second orbital and put that it would have 6 negative electrons in it. So there's our electron jazz for oxygen. Once again, we're going to do the math. 16 minus 8 tells us that there's going to be 8 neutrons present inside the nucleus. I didn't give myself all that much room to write that, but there's 8 neutrons inside of there. So that's the atom of oxygen. Next, the Lewis dot structure. It's going to be the atomic symbol, which for oxygen is O, and then a dot for every electron in the outermost shell. So that's these guys right here. So that's 6 electrons in what is known as the valence shell, which is the outermost electron orbital. Now, if you were to take a real chemistry class, they would tell you how you're supposed to place the dots. You guys are non-biology majors. I know you don't care about this that much, so I really don't care where you put the dots, as long as you put the right number of dots, and there would be 6. So dot, 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 dot. That's a dot for each electron in the valence shell for the Lewis dot structure for oxygen. So once again, all of that came off the periodic table. Once we knew all of that information, we could draw the atom as a whole, and then once we did that, we could figure out the Lewis dot structure. Next, we're going to do nitrogen. Nitrogen is N on the periodic table. So if you look up its atomic number, it's 7. The weight is 14.00, so that would round down to 14. We're going to have 7 protons. We're going to go ahead and do neutrons next, just so that I don't make my nucleus too small later on. So once again, 14 minus 7 tells us there's going to be 7 neutrons. So 7 neutrons inside the nucleus with the protons. Now we've got to place our electrons. We always start in the innermost ring. This atom is going to have 7, but the innermost ring can only hold 2 electrons. So we've got to go out 1. This one can hold up to 8. It's got 5 more electrons to place, and so we can put 5 electrons out there. Once we know that, we can do the Lewis dot structure with 5 dots. So there's the Lewis dot structure for nitrogen. Now, this is going to be the first time that I tell you this next part. Different periodic tables say different things towards the top sometimes. On the periodic table that I am looking at, one of the things that I want you to know, and we are going to say this in the notes later on, Each column on the periodic table, and by column I mean like hydrogen, lithium, sodium, potassium on down, that's a column. A column is called a group. On top of each group there's usually a Roman numeral, which on mine I've got a 1A above hydrogen. And then as I move over to the beryllium group, beryllium magnesium, that has a 2A. Skip the transition metals because they don't matter for biology too much. As you go over to boron with the atomic number 5, that's group 3A, carbon is 4A, nitrogen is 5A, oxygen is 6A, fluorine is 7A, and helium is 8A. Now here's why I'm saying that. You can use the Roman numeral group number of any element, with one exception, to kind of cheat and figure out how many electrons would be present in the valence shell. So I want you to look at nitrogen really quickly. Nitrogen, again, with that atomic number of 7, and above that group, the Roman numeral is 5A. That 5 tells you how many electrons are in the valence shell. So everything in group 5 has 5 electrons in the valence shell. Everything in group 4 has 4 electrons in the valence shell. Let's go back to the elements that we did earlier. Oxygen, it's in group 6. It should have 6 valence electrons. That's exactly what we had as we did that. And then hydrogen is in group 1. It had 1 valence electron. And so that's a way for you to check to see if you're right or wrong, is look at that group number to find out whether you're right or wrong. Okay, we're going to do one more element. This time we're going to do sodium. Now sodium is one of those elements that does not have an atomic symbol that seems to make sense. It has the atomic symbol Na, stands for natrium, which is like the Latin for sodium. If you look it up on the periodic table, it has an atomic number of 11, and it has a mass number, or an atomic weight, pardon me, of 22.98977. So that's going to round up to 23. So, drawing our element, we know it's going to have 11 positive protons. If we do the math, 23 minus 11 tells us there's going to be 12 neutrons inside the nucleus. That atomic number tells us the number of electrons. So we got to start with, it's going to have 11 total. 2 are going to go in that first shell. We still have 9 more to place, but the second orbital can only hold 8, which means we've got to add another orbital outside of that. It could also hold 8, but we only have 1 more that we have to place, and so sodium has 1 electron in the valence shell. That means sodium's Lewis dot structure is Na with 1 little dot, because it has 1 valence electron. And once again, you can check your work. What is the Roman numeral group above sodium? It's in the same group as hydrogen. It's in group 1. It should have 1 valence electron, and that's exactly what it has. So that hopefully is enough practice that you guys are going to be able to get through your basic atom stuff, but I do have some helpful things in Blackboard or Schoology for you guys to practice with there. Why is the number of electrons important? The number of electrons, especially the number of electrons in the valence shell, determine how an element is going to behave when it gets next to another element. So essentially it determines the behavior of an atom. We'll skip right past that. Next up, we're going to talk about isotopes. Now there's a reason why there's a a decimal point in the atomic weight on the elements that are in the periodic table. Like hydrogen had a weight again of 1.00794. It's because not all hydrogens are exactly the same. The most common form of hydrogen that is out there looks like what we drew earlier, where it had 1 proton and no neutrons and 1 electron. There are, however, forms of hydrogen out there that do have a neutron. If it has a neutron and a proton, it has an atomic weight of 2 instead of 1. So it's still hydrogen, it still has an atomic number of 1, it still behaves like a hydrogen, it just has a different weight. That's what an isotope is. Same element, different weight. The only way that you can make an element have a different weight is to give it a different number of neutrons. You cannot change the number of protons, because if you do that, it's not the same element anymore. So same element, different weight, because it has a different number of neutrons. Okay, next, what are radioisotopes? They're special types of isotopes that aren't stable. They will spontaneously decay, and when they do, they will release radiation into the environment. So they're isotopes that have a different weight and are unstable, will break down, and release radiation. There was an article in Science this past week about Fukushima, which was that nuclear reactor in Japan that melted down during a tsunami event. Oh my gosh, what was it, 4 years ago at this point? I think it was in 2016. They measure the amount of tritium that's in the water. Tritium is a radioisotope of hydrogen. It has a mass number of 3, so it's a hydrogen with 2 neutrons, pardon me, and then a proton. So it's an example of a radioisotope. Carbon is another one that has a radioisotope. Regular carbon is carbon-12. It has 6 protons and 6 neutrons. Carbon-14 is radioactive carbon. It has 2 extra neutrons. That unbalance that exists within the element is what makes it spontaneously decay, so that it will release that radiation. Now, how does this relate to carbon dating? As anything that is alive right now is taking in either air, if it's a plant doing photosynthesis, or consuming food, if it's an animal that eats plants that were doing photosynthesis, they are taking in a certain number of carbon-14 atoms just in the course of their day-to-day life. If we were to measure the amount of carbon-14 in your body or my body, we would get the amount that you would tend to find that is common right now. If, however, we find a sample that has been dead for thousands of years, we can measure the amount of carbon-14 that's left in that body to determine how old that body happens to be. That's because when you're dead, you're no longer eating anything, and in the case of a plant, they're no longer photosynthesizing, so they're not taking carbon-14 into their body anymore. So instead, the carbon-14 that had been in their body the moment they die, it starts that process of spontaneous decomposition and the release of radiation, even for that matter. And so we can use the amount of carbon-14 left to date how old that deceased item happens to be. It has to be really old, though. You can't use it for somebody you found in an alley 3 days ago that probably died a couple of days ago. What I want you to notice here is for carbon-14 and a half-life, which means how long it takes for half of the carbon-14 in your body to go away, is 5,700 years, so nearly 6,000 years. So if we were to find your body 6,000 years after you died, it would have 50% the amount of carbon-14 in it that it had at the moment that it died. If instead we found 25% the amount of carbon-14 in the body of a deceased organism, that means it's undergone 2 half-lives, which means that that specimen would be 11,000 years old. So you just kind of plot how much carbon-14 is left in the body to figure out how old that specimen happens to be. So here's an example that I wanted to talk about with you. This is Otzi the Iceman. He was discovered in the Alps due to glacier melt because of climate change. He was discovered back in 1991. Now, if you have ever gone mountain climbing, especially to the really tall mountains where lots of people climb them, one of the weird, morbid things that happens is when people die on that mountain, they don't bring that person down. So there's dead bodies all over Mount Everest. And in fact, they are used as landmarks. Like, once you get past that dead person with the red snow boots, you're going to turn left. Like, it's that bad. That's how many dead bodies there are up on the mountains. So when they found Otzi the Iceman, they thought it was just a climber that had been dead for a little while, not for too long. What they did, though, was they measured the amount of carbon-14 left in his system, and he had 50% the amount of carbon-14 that you would find in a modern human. So my question for you guys, look at the graph and then tell me, how old is Otzi the Iceman? In order for you to figure that out, you have to come down and figure out where does 50% cross this line, and it crosses at 1 half-life, which means he's more than 5,000 years old. He's not just some climber that was up there recently. He's been there for thousands of years at this point. He's a very fascinating person. He was killed. He was shot with a couple of arrows in the back, but he was doing pretty well for himself before he was killed because he had a full stomach when he died. Okay. Next up, you have how many electrons can each energy level or orbital hold. I'm only going to hold you responsible for the first 3 orbitals, and we kind of talked about this earlier, but the first one can hold 2, the next one out can hold 8, the next one out can hold 8, and so 2, 8, and 8. Kind of recommend you draw that as the circles. That might help you understand it, and then just remember you always start at the innermost circle, and then once that one's full, you move out to the next one. Once that one's full, you move out to the next one. Alright, so we're going to come back to this group versus period sort of a thing. Let's look at the information provided in the periodic table. A group is a column. So all of these are in group 1. And there's that Roman numeral that I was talking about earlier. Beryllium, magnesium, calcium on down, those are in group 2. We are usually going to ignore the transition metals because, again, they're not, for the most part, important for biology. So then we come back over here and you get group 3, group 4, group 5, group 6, group 7, and then that's group 8. The other thing that I want you to know about the groups is what I did already say. The group that an element belongs in tells you how many valence electrons an atom has. So everything from hydrogen, lithium, sodium on down, they all have 1 electron in the outermost shell, or 1 valence electron. Everything in group 2, 2 valence electrons, and so on. So the group number tells you how many valence electrons an atom has. I'm going to switch colors to do this next little thing. Okay, next. The horizontal rows, and hydrogen and helium, they're in a row, it's just a short row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they're a row. A row is called a period, and so this is the first period, this is the second period, this is the third period. I said earlier, I'm only going to hold you responsible for learning the top 3 periods' atomic symbols. So that means these are the elements that you should learn the names to and the symbols to. So H is hydrogen, Li is lithium, and so on. There are a few other elements that are scattered around that you should go ahead and learn the names to because they do matter for biology. Let's see, iodine is necessary for making thyroid hormone. Mercury is an important poison. It's also the unit for blood pressure measurement is millimeters of mercury. Iron is very important for blood cell formation. If you don't get enough of it, you end up with anemia. What else do I usually make you guys learn? Calcium and potassium, which I circled those out of the order that I said them. Those 2 elements are important for our bodies. In fact, calcium is arguably the most important mineral that you need in your body, and not just for strong bones. Your muscles can't contract without it. Your nervous system can't think without it. You need calcium for a whole slew of reasons. Anything else that I want you guys to know? I do usually go ahead and throw lead in there. Lead's another one of those toxins. It used to be in gasoline. Now it's not anymore. It used to be in paint. Now it's not, because we know it happens to be super toxic to the nervous system. I think that's pretty much all that I want you to know. So top 3 periods and then those few elements that I circled in there are going to be important when it comes to biology. The other thing that I want you to know about periods, the period that an element sits in tells you how many electron shells an element is going to have. So everything in the first period only has 1 orbital of electrons. Everything in the second period has 2 electron orbitals. And if you go back and you look at what we drew earlier for all of our elements, you'll see that we drew them exactly right. Everything in period 3 has 3 electron orbitals. We drew sodium, you'll notice it had 3 orbitals. And so it's another way to verify that you're doing things right, is to pay attention to what the periodic table is telling you. This is what I said earlier. If you didn't get anything I said, just pause this and make sure you write it down. When are elements stable? It's when an element has a full valence shell of electrons. And so if there's only 1 electron orbital, then the element's stable if there's 2 electrons in that shell. Since the next one out can hold up to 8 electrons, it means the element that has 8 electrons in the second shell, that's going to be the stable element. Anytime the valence shell is not full of electrons, that's going to be an atom that wants to interact with another atom so that it can try to get to 8 electrons in the valence shell. That's called the octet rule, which is the next thing. So it's called the octet rule because most of your orbitals can hold 8 electrons, and octet means 8. It does not hold true for the elements that are in the first period because they only get 1 shell, and that shell can't hold 8. It can only hold 2. But generally speaking, for most of the elements on the periodic table, not hydrogen and helium, but most of the other ones, they're going to be what I'm going to call happy or unreactive if they have a full octet of electrons in that valence shell. If they don't, they're going to do whatever it takes to get to 8 electrons. The analogy that I usually give you guys here, or the stupid memory trick that I give, is I want you to imagine that all the kids in a kindergarten class are playing on the playground, and every kid is happy if it has 8 toys to play with on the playground. If you have a kid who doesn't have 8 electrons, it will or toys, it will do whatever it takes to get to 8 electrons in the valence shell. So they'll steal toys, they'll throw away toys, they'll share toys, whatever it takes that allows it to get the 8 that it wants to play with, that's what it's going to do. And that's what an atom is going to do as well. So we can give away, we can steal, we can share. Those are basically the options that we have to try to satisfy the octet rule. Oh, that's actually where I'm going to stop this video. We'll pick up with ions next time.